Today, to customers and colleagues around the world, the modern copper concentrator can process in excess of 50 million tons per annum of run-of-mine feed. So typically 2 or 3 SAG mills, and these can be up to 40 foot in diameter, are employed for the milling process. The mill discharge needs to be screened in order to remove oversize, in order to protect the pumps and the cyclones. So my talk of today focuses on the use of a trommel screen for this purpose. Multotec, who is an OEM of trommels, supply these to both end users and mill OEMs around the world. 20 minutes allows us only an overview of the topic. It's certainly one of the more challenging screen duties, and we're going to define this duty in more detail. Given the abrasive nature of the ore, screen media is always going to be a critical component of the SAG mill trommel. I will advise on the option of rubber or steel trommels. We will focus on retention systems that are there to turn turbulent flow into laminar flow. And lastly, I will ask the question, but can the vibrating screen not perhaps perform the same duty? I quite fancy this description of what the SAG mill trommel does. It comes from the famous Vancouver Mill Conference, and the authors, Doug Van Nel and Stephen Thompson, felt that the classification trommel screen provides a mechanism to efficiently sort large volumes of SAG mill product with relatively simple equipment. Efficient classification, that could be debatable. Does the trommel really need to be 90% efficient? The key words for me are large volumes and simple equipment. To set the tone for my discussion, a few pictures from sites around the world. This one is from Central Africa. 2 40-foot SAG mills in combination with 5-meter diameter trommels, each capable of screening 4,500 tons per hour of solids. The next one comes from South America. 3 SAG trommels. These operate on a 100 million ton per annum copper concentrator. Personally, I've not seen much bigger trommels during my travels. Then let's just remind ourselves of the different types of trommel screen. The SAG mill trommel, which we're going to discuss, is one of the 2 types that we call driven trommels. We need to distinguish these from self-driven trommels. These self-driven trommels can perform a variety of duties. They're versatile equipment, but more often than not, they're used to remove oversized material, organic material, from mineral sands applications. And then lastly, not very common, we find the trommel on a scrubber, where it is required to perform a sizing duty. It's important to note at this stage that the SAG mill and the ball mill trommel attaches to the trunnion of a mill. And I make this point because Multotec will always engage and work in collaboration with the mill OEM as far as the design of the trommel is concerned. Next up, we have a picture of 2 rather large SAG trommels in some of our factories. Now, you might be familiar with modular, or what we call 1 by 1 foot screen media. However, when trommels become this large, we have to resort to what we call a shell play design, and we need to do this for load distribution and FEA reasons. And these large shell play designs call for not for 1x1 foot, but for large compression molded rubber screen media. The other reason is a practical one. Who wants to replace 600 odd screen panels on a shutdown day? I've mentioned the second type of trommel screen, which is a self-driven trommel. These units can become extremely large. What you see in picture are two 15-meter long trommels operating in West Africa. I believe it's in Ghana, in a mineral sands operation. So we're talking of a challenging screen duty, and there's a number of reasons for this. First of all, these trommels are subjected to anywhere between 4,000 and 5,000 tons of fresh feed per hour. Now at the recirculating load, and all of the 7,000 cubic meters of slurry needs to pass through that aperture that you see in the trunnion. And it only spells one thing in capital letters: turbulent flow. This is a 4,000 ton per hour fresh feed application in Central Africa. Now we know that proper drainage is only going to commence once we've established laminar flow. So how do we turn what you've just seen, that turbulent flow, into laminar flow? More about that just in a moment. Challenging screen duty. Compared to the ball mill, the sag mill sees considerably more oversized material. Up to 20% of fresh feed can be oversized when we talk about sag mill trommels. So taking the lump size and the bond work index, which could be more than 15 kilowatt hour per ton, into account, we can see that heavy duty screen media is required on sag mill trommels. And what you see in picture is a typical sag mill discharge. This, however, is not typical, but they do escape from the mill. This is a steel trommel with a 19 mil thick shell, and the wear life achieved on this was only in the region of 8 weeks, a copper mine in Central Africa. Since we've replaced this with heavy duty 80 millimeter thick rubber panels, we were able to increase that wear life from 8 weeks to 20 weeks. So I think the message is clear. We need appropriate screen media for the sag mill trommel. The general rule is that the use of polyurethanes and injection molded rubbers is only on ball mills. When it comes to sag mills, we need compression molded rubber in special formulated rubber compounds. Our experience is that steel alloys will typically only last 50% of the wear life that we can achieve with dedicated rubber screen panels. On the left-hand side of the slide, you have a 30 millimeter thick typical ball mill trommel panel, and what you see on the right-hand side is a compression molded heavy duty panel that has been designed for the sag mill duty. Now, if you think back to a previous slide, you'll remember that I said the frame design of large trommels calls for larger screen media. So in picture, you have a typical sag mill trommel screen. And in our experience, when we deal with these large copper concentrators, the shutdown frequency is in the region of 12 weeks. And that is then the minimum wear life requirement on a sag mill trommel. However, in many instances, we've been able to straddle this frequency of 12 weeks, and we supply media that can run for 24 weeks. This is really what we're aiming for today, a well-protected trunnion and trommel screen dressed in 80 mm thick compression molded rubber panels and screen media. And this promises then, as I've said, in excess of 20 weeks wear life. As a supplier, this is what you don't want to see. Imagine 10,000 tons per hour through 2 mills. Imagine the revenue loss per hour when a mill has to stop because of screen media. Apologies. So the design is not only about working depth and dam thickness, you also need to get the chemistry right. Abrasion resistance could be the successful recipe on one side, but elasticity and tensile strength could be required at the following site. Mechanical design of the panel is an important component of overall screen design. In this instance, it's clear that the internal support frame was lacking. The panel was unable to carry the oversized load. It's in the process of sagging and the panels are pulling apart. So the internal frame needs to cater for items like lump size, trommel load, and drop height from the trunnion. More examples of school fees paid. One of the challenges that I've mentioned is turbulent flow. And these modern design of pulp lifters and vortex discharges can cause turbulent flow conditions. In this example, the M12 bolts were not nearly sufficient to attach the bolts and scrolls in picture. A simple slide that tells an important story. As far as safe installation goes, the safest method, for obvious reasons, is still to change media from the inside of the trommel. And that is the reason why the pin and sleeve and the various clip-in type panels remain the more popular designs. So why can you not consider a steel trommel for your sag mill? You can. We supply both at Multotec. The specific site in Africa changed from steel to rubber, and the result is that they've managed to more than double wear life. So this picture tells the story. If you do employ steel, you're more likely to replace trommel screens much more often. Our experience is that heavy-duty rubber media will last at least twice as long as a steel trommel with a typical 20 mm shell thickness. And we've really conducted a number of case studies on African copper mines, and the life cycle cost of steel is roughly double that of rubber. So steel trommels are utilized where rubber media lacks the necessary capacity to perform the duty, but it does come at the expense of higher operating cost. You can clearly see what I mean with superior open area. This trommel in picture has open area in the region of 40%. Important to note, though, that steel trommels are not modular in design. And the implication is that you're not going to replace screen media, but you're going to dispose of the entire unit when it has worn out. So apart from this, the relative short wear life contributes to the higher life cycle cost. You need to realize that the rigid nature of steel can cause significantly more pegging, and it's therefore critical to keep an eye on the percentage of near-size material in the feed to the trommel. This picture comes from Asanko Gold in Ghana. Think back to the video and the challenge of turbulent flow, which is detrimental to drainage. We need to create some form of retention mechanism, and this comes in the form of a wear bar and scroll configuration. These perform two duties. They perform laminar flow, but they're also there to transport the solids fraction out of the trommel, which essentially is a horizontal installation. The incorrect layout or design of this system of wear bars and scrolls can compromise the efficiency of a well-designed trommel system. And look at the drop from trunnion to trommel. It's more than 1.5 meters in this instance, and once again, it spells turbulent issues. This specific one turned into a bit of an engineering project. Rocky software was used to model the exact discharge trajectory of slurry out of the mill, and the result was the combination of angled baffle plates and wear bars that you see in the left-hand picture. Speaking of various scroll heights, they really do not come much taller of this, a buried copper mine in Africa. Important to note that scrolls this high needs to be attached to the trommel steel frame and not the screen media. So the scroll height is not only determined by the solids loading, but more importantly also by the slurry discharge trajectory. So we need to optimize this for both height and for position in order to create laminar flow conditions. Finite element analysis. Considering the size and the complexity of these large trommel frames, and you can see the amount of welding, it's imperative to perform a finite element analysis. We designed for 10 million fatigue cycles, as this promises indefinite life in theory. And on these large trommels, which rotate in the order of 10 revolutions per minute, it takes about 24 months to reach that 10 million fatigue cycles. In our experience, a rubber-lined trommel frame that is well maintained by the customer lasts up to 5 years. So where do these stresses originate from? We need to cater and design for them. They come from the deformation of the supporting trunnion. There's the weight of the trommel itself. Some of these trommel systems, frame and panels, can weigh in excess of 25 tons. There's also the live load that has an influence. I've mentioned feed tonnages up to 5,000 tons per hour. And then these are the type of dramatic failures that can occur when the FEA is not performed. Fortunately, this is not a Multotec frame. The picture comes from a South African platinum mine. So it's critical for the customer to verify that his supplier is able to perform these type of FEAs. It's also important that the customer supply the correct process data to the supplier to allow him to perform finite element analysis. So can you not rather utilize a vibrating screen for this duty? They're a common sight on ball mills, but not so much on sag mills. The ones that we do come across operate in combination with a sag mill trommel. I believe the comparison looks as follows. Trommels are simple and robust. They do not require specialized skills. There's no drive mechanism. There's no isolation to talk about. There's no lubrication. There's no V-belts. There's no garden shaft. They're simple and they're robust. A rotable unit, when it's dressed with panels, will take less time to replace. With a vibrating screen, there's feed chutes that needs to be removed. It's a longer process. Trommels do not generate the type of dynamic loads we encounter on vibrating screens. Therefore, they require less civils when it comes to the installation. Trommels are more prone to pegging as they do not have the benefit of a stroke that is being created by the vibrating screen. And this is my personal opinion. They're possibly less efficient at fines removal because they do not agree the same level of stratification. And we don't have the same type of control that we can exercise over the discharge bed like we have on vibrating screens. In order to replace a trommel screen that is capable of screening 4,500 tons, according to my sizing, you'll need 2 of these rather large vibrating screens. These are in the region of 3 or 3.6 meters wide. This concludes my presentation of this afternoon. Thank you for listening. I trust that you found it interesting. Goodbye for now.